Hello, Chem 130 students at GCC. Welcome to Chapter 5. So you've just learned a little bit about the atom, and now we're going to talk about atomic structure. But first I'm going to start talking about light, and then I'm going to connect that back to the atom. So light from the sun or from light bulbs exists as waves. You've probably heard this in a science class before. So we have waves of light energy. There's some properties about a light wave you need to know. First thing is the wavelength. That is the distance from one peak to the next peak. Wavelength is given the Greek letter lambda as its symbol. So you can see lambda there in red. It's a Greek letter lambda, and it represents the wavelength, which again is the peak to peak distance. Another property of a wave is its frequency. That is symbolized by the Greek letter nu. It looks like a V, but it's tilted a little bit. So frequency is kind of like the beat of the wave. It is how many peaks pass by a certain point in a second. So it's the number of waves that go by in a second. So if we have a little bitty short wavelength, then a whole bunch of waves go by in a second, and the frequency is fast. If we have a long wavelength, then during a second, only a couple of waves may go by, theoretically speaking. So the frequency is slower. It's a low frequency. So again, the frequency is kind of like that beat, the beat for the wave. All right, let's look at two waves and compare them. On the top, we have a longer wavelength. Again, that means the frequency is lower. Now, energy is directly proportional to frequency, so it is also lower if the frequency is lower. So that longer wavelength has a frequency of like beep, 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 beep. Now, the bottom wave has a much shorter wavelength. That makes the frequency go up and be high. So the energy, which is proportional to the frequency, is also high. Now the short wavelength, its frequency is more like beep, 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 beep. So it has a higher frequency. Now let's see if you have learned anything. I have right here wave A and wave B. Which wave has higher energy? I hope you said wave B. Wave B has higher energy. Good job. Which wave has lower frequency? I hope you said wave A. That's correct. I'm going to add another question in. Which wave has shorter wavelength? Wave B, right? Shorter wavelength. Very good. Which wave has the lower energy? Wave A, right? All right, good job. I think you've got it. Good job. Now, let's discuss all the different types of waves. They are all included in the electromagnetic spectrum. So the electromagnetic spectrum just tells us what the type of wave is from high energy to low energy. Over on the high energy side, we have gamma rays. Those are high energy and dangerous. If you're exposed to a lot of gamma rays, you might get cancer. Next to gamma rays, we have X-rays. You may have had an X-ray before on your teeth or on a broken bone. X-rays are also pretty high energy. If you have a lot of X-rays, there's a very small chance you could get cancer, but it's very, very, very small. Next to that, we have UV or ultraviolet waves. Those are dangerous still because when they hit your skin, if you're out in the sun a long time, they can cause skin cancer if you're repeatedly burned a lot. Your chances of skin cancer go up. So ultraviolet can also be kind of dangerous if you have too many sunburns. Next to that is visible. That's what a human eye detects, the rainbow of colors. Visible aren't dangerous. They hit our eyes, they hit us all the time. We have visible light waves from the sun and from light bulbs. They're not dangerous. Next to visible, we have IR, or infrared. Those are heat waves. Next to that, getting lower in energy still is microwaves, like in a microwave oven. And then last on our list with the longest wavelength and lowest energy is radio waves. Now, radio waves hit us all the time. We're not melting, we're fine. So radio waves, microwaves, infrared, and visible, they hit us all the time. They're not as dangerous as the first three. Now, my next question is, which waves travel the fastest? I bet you said gamma, and that's a guess, but let's see if it's right. Let's have a race. Let's have a race with some high energy waves and a low energy wave. Ready? Let's go. What'd you notice? They go forward at the same speed. Now the high energy wave is high energy because it has a higher frequency. The low energy had a lower frequency, but they went forward at the same speed. All light travels at the same speed. What speed is that? I gave you a hint. Light speed, right? All waves travel at light speed. Remember that. And finally, I want you to remember these in order: gamma, X-ray, UV, visible, IR, microwave, radio. Remember the electromagnetic spectrum in order. You will be questioned about that. All right, remember how we had a couple of scientists back in chapter 4 that we talked about? Well, we're going to bring on a couple of more scientists in this chapter. So around 1900, the scientist Max Planck proposed the idea that energy was emitted in small bundles called quanta. So he was saying light energy isn't a wave, it's like a little beam of energy. He said an individual unit of light energy was a photon. Now you may have heard that word used in science fiction, like photon torpedoes, photon ray guns. So he is the idea who came up with the idea of photon. So you need to remember that, Max Planck. So he said a little individual light energy is a photon. So which is it? Is light a wave, or is it a particle beam made of photons? Well, the answer is both. Those are just two models we use to describe light. And depending on the situation, sometimes light is like a wave, and sometimes it's like a particle beam. So it depends on the situation which model fits better. So we can say light is wave-ish and particle-ish at the same time. Now I have a new word for you, quantized. It's just a vocabulary word. Quantized means exists in levels, not continuous. Let me show you a picture. The ramp is continuous. When you roll a ball down a ramp, it goes down smoothly. It's continuous. However, if we were going to roll a ball down stairs or steps, it would bounce. It's not smooth. It's not continuous. Steps or stairs are quantized. We have a step, and then we have the next step up, but you can't step in between. Nothing's there. So we have a step, nothing, the next step, and then nowhere to step, and the next step, etc. You can only put your foot on the step, not in between the steps. There's nothing at that height. What else is quantized? What else exists in levels? Well, how do you get to your roof? A ladder. A ladder also has kind of like steps, rungs of the ladder. You can put your foot here, you can put your foot here, but you can't put it in between. There's nothing there. Quantized, it has levels. What about a bookshelf? You can put your book on this shelf or on the next shelf, but you can't put it in between. It'll fall down. Bookshelves are quantized. They have levels. What about a tall building? Yeah, you have floors, first floor, second floor, third floor, fourth floor. You can stand on the first floor. You can stand on the second floor, but you can't stand in between. You'd fall down. So again, a tall building is quantized. It has levels. So it's just a vocabulary word. Quantized means exists in levels, which brings us to the next scientist, Niels Bohr, back in 1913, so over 100 years ago, said that electrons go around the nucleus in discrete energy levels. So they're quantized. Electrons are quantized. Wow. So he's basically saying that an electron can exist on a level or another level, but not in between. So Bohr's model of the atom, again 100 years ago, was that electrons orbit around the nucleus, kind of like planets orbit around the sun, but in 3 dimensions. So you can think of this orbit as a sphere around the nucleus. The electron can travel anywhere on this sphere. Now, we're going to call these orbit spheres energy levels. In high school, you call them shells. You may have seen that before. But we're going to call them energy levels. So each energy level is a specific radius or distance from the nucleus and has a certain amount of energy. So here's a little picture. You may have seen something like this before. The nucleus is in the middle. Then we have empty space until we get to level 1, the first sphere. Then we have empty space till we get to level 2, the second sphere around the nucleus. Then we have empty space till we get to level 3, the third sphere around the nucleus. And the electrons have to be on those levels. They cannot be in between. Wow, how could Bohr possibly know that? Well, that's the topic of my next video. So hang in there, take a little break, GCC.